Okay, welcome to topic 6, redox reactions, 6.1, which is concepts of oxidation and reduction. This is the first video in topic 6. In this video, I will be covering a range of reactions, including reactions of metals, combustion, and electrochemical process that can be considered as redox reactions. So that's really an introduction of what redox can be. And also we'll look at oxidation and reduction can be defined in terms of combustion with oxygen, transfer of electrons, or change in oxidation number. Now, to talk about that, we need to look at what oxidation number is, and we're going to spend a bit of time on that. So let's have a look. So, redox interaction. Now, what is redox? It's a mixed word of reduction and oxidation. So, if you combine those words, you get redox. Apple browning is an oxidation. You hear the word in normal day-to-day term as well. When a cut apple is exposed to the air, you get oxidation. So, apple can be brown. Oxygen exchange in bloodstream. Now, oxygen has got hemoglobin, which has got the iron, Fe, iron at the center, and that changes its oxidation state from Fe2 plus to Fe3 plus to accept oxygen, and then release that oxygen at the end of your fingertip or whenever. And when that happens, Fe3 plus becomes Fe2 plus. That's an oxidation, so redox reaction as well. Bleach, hydrogen peroxide base, for example. When hydrogen peroxide releases oxygen, it oxidizes stains, and then stain will change color. Again, that's a redox reaction. Water chlorination using ClO, it's called hypochlorite ion. Water is purified with adding chlorine gas to it, and then by having hypochloric acid, you can kill the bacteria or algae that might get into your water system. Corrosion or rusting, same thing. Fe can become Fe2 plus or 3 plus. That's going to be rust, appearing as rust. Battery discharging and recharging, that is a reaction that you would even do as practical. Galvanizing metal, you would hear galvanized zinc sheet for roofing and stuff. By having zinc layer, it lasts longer instead of just steel. Metal production uses what's called electrolysis. So you extract metal from say copper ore or zinc ore, and the last process is usually the electrolysis, which uses redox reaction. Let's talk about what oxidation numbers are. So oxidation numbers are assigned to keep track of how many electrons have moved, or should say lost or gained by a species. So for example, Fe ion, I should have put down state, that's a solid ion. When it loses electrons, 3 electrons in this case, you get Fe3 plus. Now, this is considered to be a loss of electron, and we'll talk about that, but that's an oxidation reaction. Fe is now oxidized. The oxidation numbers given is 3 plus. So maybe you want to circle 3 plus as oxidation number here. And general concept of oxidation number is, well, you will see this video later in the lesson, or you can watch that first. Okay. How do you assign oxidation number? Here are some rules. So maybe you should put the heading saying rules in writing oxidation numbers. Firstly, hydrogen has an oxidation number of +1 when bonded to non-metals. When it's bonded to non-metals, sometimes it can have -1, but usually it's +1. Oxygen has oxidation number of -2 pretty much all the time, except for these two things, F2O and H2O2. You can look at the oxidation number of oxygen in F2O or H2O2 later. 3. Free elements have an oxidation number of 0. So if it's in a natural state, say if it's a sodium or oxygen, which is O2, or chlorine, which is CO2, they all have oxidation number of 0 per atom. 4. The sum of the oxidation numbers in the neutral group, which should be 0. So for example, if you have got H2O, the whole species as a whole, the oxidation number is 0. But H would have +1 and oxygen would have -2. And they should balance out. Same goes for, say, I don't know, magnesium oxide, maybe. Magnesium, as you know, it becomes 2+ when it's ionized. When it loses electrons, they get transferred to oxygen, and oxygen would have 2-. So 2+, 2-. If you add them up, you should get 0, shouldn't it? We'll write that down as an example later. The sum of the oxidation number, number 5, in the polyatomic ion is equal to the charge of the ion. We will determine oxidation number of each of these species, each element in these species in class. So please write it down and be ready for the lesson. Final slide of this video. Now, what defines the electron transfer and how many electrons would move or to be shared within a species depend on electronegativity of each atom. Remember which element has got the highest electronegativity and which way the trend goes. Hopefully you're pointing at that way. So top right corner would be, so the fluorine would have the highest electronegativity. Yeah. Atoms with higher electronegativity gain control of the electrons. They want to gain electrons more than other species. And atoms with lower electronegativity lose control. They would happily give out its electrons to the one with higher electronegativity. This can be used to determine how many electrons each atom gained or lost. Therefore, you can determine the oxidation number within a species. So for example, 2SO2 plus O2, that became SO3. You should remember it from acid rain part of it before. What are the oxidation numbers and how they changed before and after? Okay, so from before the reaction, SO2, because you know the oxygen is going to be -2. Why? Because oxygen has higher electronegativity. Therefore, sulfur needs to have +4 in this case. Oxygen in an element, if you remember, per atom, the oxidation number is 0. Electrons are shared, hasn't moved yet. After the reaction, what happens? Now, oxygen again has got the higher electronegativity compared to sulfur. Therefore, oxygen would still be -2. But there are 3 lots of them. So -2 times 3 equals to what? It's -6. As a whole species of SO3, it needs to be 0. The charge needs to be 0. Therefore, sulfur's oxidation number has to be +6 in this case. And you can see that sulfur's oxidation number changed from +4 to +6. I'll zoom into here. This is due to oxygen having higher electronegativity compared to sulfur, and that's the reason why the oxygen has gained control over the electrons in sulfur. Please note again that the oxidation number shown here is applied per atom. In SO3, oxidation number is -2 and not -6. Okay, oxygen per atom is going to be -2, and that's how you show the oxidation number. We need to know all this for you to move on to how redox reaction works.